Kia ora. In this video, we're going to be talking about stability and determinacy. Stability, you would have already been slightly introduced to back in the first lecture when I built a triangle and I built a square. And the triangle stayed up when I tried to push it to the side, but the square collapsed. So we concluded that the triangle was stable, the square was not. And that's a quick introduction to stability. Stability is where a structure will collapse under its own self-weight. There are two types of stability: external stability and internal stability. Let's have a look at external stability. So in this example, I'm going to apply a load F going sideways. Now this is an external load alongside this other external load P. Now external stability is where the stability of the structure is provided by the reactions or the supports of that structure. The supports of this structure are this pin connection and this roller connection. As we know, a roller connection only has a vertical reaction, whereas a pin connection has a vertical reaction and a horizontal reaction. So now looking at the structure, given the two external forces that we've applied, F and P, the reactions of this structure are adequate to counteract both F and P, because the pin and the roller support provide upwards reaction to go against the P force, and that pin connection has a horizontal reaction to go against that F force. So external stability is when stability of the structure is provided by the supports or the reactions. The other one is internal stability. And internal stability is where the internal members or the individual members or the system of members within the truss provide the stability. So let's have a look at an example. This second figure here just demonstrates that, we have two roller supports. And so if we were to apply a horizontal force, because these two reactions only have each vertical forces to counteract that P force, any horizontal force on this structure, this truss would just go flying to the left. So that means it's externally unstable. But anyway, let's go to internal stability. As you can see, we have a square. And as you know, squares are unstable. But why? Let's have a look at load P, and let's consider how load P is transferred through to each of these supports. Well, first load P would come through here, and it would come through here, through to the support. But what about on the other side? It would come through here. If we consider forces, sum of forces in the y direction, the force from this member needs to be counteracted by this member. So now let's come to this joint and consider the forces in the y direction. Well, because this force here, this member here has a force, then this member here must also have a force. Now let's go to this joint. Let's consider the sum of forces in the y direction again. Because this force here has a force in the y direction, this joint must have to be counteracted by another force in the y direction. But there is no member there. Okay, so that means this joint is actually not stable, meaning that it only has one force acting in the y direction, meaning that it would be pulled down or pushed up. So that's what instability means. It means that the internal members in the truss, or it means that there aren't enough internal members in the truss to provide enough load paths for the load from load P to be transferred through to the supports. This is a quick exercise for you. And I just want you to determine whether these structures are stable or unstable. Let's have a look. Well, first I invite you to pause and try this exercise for yourself before I actually show you the results. So let's go have a look at this first one. Oops, okay. Now, we do have a square here, right? And we know that squares are unstable. But that's not the only thing we need to look at. If we had a look at what was behind it, so this structure right here, we can see that that is a stable structure because it consists only of triangles, right? Which means that actually these two joints here can't move relative to each other. They can't move closer, they can't move further apart from each other. That means that this square will not change its shape no matter what. And because that square is the only part where we thought might have been unstable, this structure is in fact stable. Now, just a quick thought. What happens if we took this member out? What would happen? Well, it would mean that we have a stable structure in this triangle, stable structure in this triangle, okay? But what was once a stable shape in this whole back area here is now two stable structures connected only by one little unstable hinge right here. So now this back end here is unstable. And now these two joints can actually move further apart or closer to each other. So that means the structure is now unstable. Let's have a look at the next one. Again, pause if you want to. We know that a shape such as a square or diamond is unstable. We see here two stable triangles, but what's between them is not stable. So that means this whole thing is unstable. Now, if I were to try be a cool guy and draw the collapsed shape of both of these shapes, or both of these structures, the first one might look like, first of all, let's draw the connection, the pin connection. Now, this square here would probably collapse into a straight line. So it might go something like that. And then these two things, those are the two these are those two triangles. And then these are the other triangles. Those are those two triangles, right? So because this member here isn't there, these two joints, hopefully this isn't too messy, it probably is. Get rid of that. So if this member wasn't there, then these two joints would most likely collapse on each other. These two joints would most likely run away from each other, and this joint would come to touch this joint. I hope that makes sense, but it's not really relevant, it's just a bit of fun. This next one, well, it would probably fall, so we have our two supports, and these two joints would probably come to touch one another, so it would probably end up looking like that. Okay, because these two here would run away from each other. Determinacy. So determinacy is essentially you being able to analyze a structure given only these three equations. In the case of a truss, given only these two equations, because we know everything is either in tension or compression, there's no moment. So a statically determinate truss is one that you can analyze, so you can do method of joints and find the demands on each member only by using those two equations. Yeah. Again, we have external determinacy and internal determinacy. External is where your reactions, external determinacy is where your reactions are only providing enough, when your supports are only providing enough reactions such that you can determine the magnitude of those reactions. So in this case, we have two supports, one roller and one pin. The pin has two reactions and the roller has one reaction. Okay, so now we have three unknowns, but we also have three equations. We have forces in the y, forces in the x, and sum of moments. So of course, we can do sum of moments about one of these supports and then find the reaction on one of these supports, and then we can find the other reaction. I hope you know how to do that, but yeah, that'll be covered in the next video. So external indeterminacy is where the reactions supports provide too many reactions for you to calculate. So if there were 4 unknown reactions and we only had 3 equations, then we wouldn't be able to determine the reactions from those supports. Take this one for instance. Here we have a pin with a vertical and horizontal reaction. We have a roller with a vertical reaction and another roller with a vertical reaction. We now have 4 reactions that we need to calculate, but we only have 3 equations. So that means we're going to have to do some more complicated maths, like simultaneous equations, which we don't want to do this year. So when we have too many reactions, that means we are externally indeterminate, or your truss is externally indeterminate. When we only have 3 reactions, that means we are externally determinate, which is good. Now, internal determinacy is where the structure, or where the members inside the structure allow you to be able to do method of joints only by using the sum of forces in the y direction and sum of forces in the x direction. Internal indeterminacy is where there are too many supports, or too many members, sorry. So it's the opposite of unstable. So before an instability, we didn't have enough members inside the truss, but internal indeterminacy, which is bad, is when we have too many members in the truss. So let's look at this example here. Again, the load will go through there. On the other side, the load will come through this member and then through this member, okay? And then it can go through this member and this member. Now, the thing wrong with that is that if we were to isolate this joint, we have a member coming through here, one there, one there, one there, one there. Now we have force there, and we need a force that can counteract that force. Or we need a member that can counteract that force. But in fact, we have two members that can counteract that force. Because we only have two equations, because we have two equations and two unknowns, we cannot calculate. Moving on to determinacy. Essentially, determinacy is where we can analyze a structure, so we can do methodal joints only using these three equations: sum of forces in the x, y, and sum of moments about a axis. Again, we have two versions of determinacy: external determinacy and internal determinacy. Let's first look at external determinacy. When a structure is externally determinate, that means the reactions, or the supports of that structure provide just enough reactions for us to be able to calculate it using our three equilibrium equations. These three equations right here. If a structure is externally indeterminate, that means the supports of that structure are providing too many reactions, okay? Too many reactions for us to calculate given only our three equations right here. Let's have a look at an example. So in this first example, now this is, spoiler alert, externally determinate. If we were to go sum of moments about this joint right here, or this support right here, we would easily be able to find this vertical reaction from this pin support. Finally, if we were to use sum of forces in the y direction, we could easily find the vertical reaction at that support. Now, if there were a horizontal force F applied to this, we know that this pin support has a reaction, and if we do sum of forces in the x direction, then the reaction at this pin support would just be equal to F. Let's have a look at an indeterminate case. So indeterminacy is where the reactions, or the supports, are providing too many reactions for us to calculate. We see that there are two roller supports and one pin support. That means we, in fact, have 4 reactions, because the pin provides 2 and each of those rollers provide 1 reaction. Now, if we were to go and you try to use our sum of moments, so we tried to do sum of moments about here equal to 0. In that one equation, we in fact have two unknowns in this reaction and this reaction. So that means we won't be able to find either of these reactions. And that's why it's indeterminate, because we can't calculate it using only our three equations. Let's have a look at internal indeterminacy. So internal indeterminacy is when there are too many members inside the truss that we actually can't use method of joints, or we can't actually use just our sum of forces in the y direction and sum of forces in the x direction. Now remember, when you're doing method of joints, analyzing a truss, and we're assuming that only tension and compression exists in those members, then sum of forces in x and sum of forces in y are the only two equations we need to know. When there are too many members in a truss, that means when we arrive at some of these joints, like this one right here, there are too many unknowns for us to calculate using only our two equations. So it's the opposite to internal instability, which is when we didn't have enough members inside the truss, okay, compared to now when we have too many members in the truss. So for instance, if we had a joint, I'm going to draw a hypothetical joint, and we know, let's say we know that force, but then we also have two members like that, which can counteract that force. Okay, usually when we do sum of forces in the y direction, we can use this one, okay, and so how do we know whether a structure is internally or externally indeterminate, or internally or externally stable? Well, there's fortunately for us, there's a calculation that we can use, and it is these three calculations right here. M is equal to the number of members inside the truss. Okay. J is equal to the number of joints, and R is equal to the number of reactions. So let's use this truss right here as an example. M is equal to M is equal to 1, 2, 3, 4, 5, 6, 18. J is equal to 10. And R is equal to 3. Now let's go and use our equation M equals 2J minus R. Well, M is 18, 2J is 20, minus R is 17. So that means 2J minus R is in fact less than M, okay, which would be this guy right here. No, yeah, it is this guy right here, which is indeterminate. In our unstable case, remember when these two weren't there and we had a square right there that was unstable, M would equal 16, right? So that means 2j minus r would be 17, but m would be 16. And so we would have this case right here, where our truss, where m is less than 2j minus r, meaning that the truss will collapse. What we want in our truss is this case, where m equals 2j minus r. And in your assignment, that's a requirement for you. Here are some quick exercises for you. So just count the members, count the joints, count the reactions, and then determine whether these trusses are unstable, indeterminate, or stable and determinate. That's the video for this, and that's this video. And that's the end of this video. Thank you.